So if you mind your P's and Q's, remember which is which. And your focal length on this one was 15 centimeters. So solving algebraically, for Q, you get negative 13.1 centimeters. From that, what you can tell is that this is virtual. Negative Q means a virtual image because it's forming behind the mirror. Yes, ma'am?
I thought that was based.
So the question was, isn't real versus virtual based on the Q? No, that's based on M. So Q just determines real or virtual. So a negative Q is a virtual image. It's forming behind the mirror. A positive Q is a real image. It's forming in front of the mirror. M, your magnification, is negative Q over P. When we do that, we get a positive 1.8750 to infinity. With sig figs, that ends up as 1.88. So it's positive. That means positive magnification means an upright image. And a magnification larger than 1 means an enlarged image. So you got a point for this, an imaginary point, a point for this, and then a point for knowing, and this is key because I had one or two people who fudged themselves, and I did take off a point. It's an imaginary point. It doesn't matter. Knowing from the numbers that this is virtual, upright, and enlarged. Okay? So the ray tracing should really just be used to confirm what you've already figured out mathematically. Or if you're doing like a sort of a rough out on something and you don't need exact numbers, ray tracings are great. But to get real exact numbers, you want to do the math. Let's look at the ray tracing for this one. This, and again, these were imaginary points. I made the ray tracing worth 1 imaginary point. Okay, so here's how the ray tracing for this one looks. These are the hardest ray tracings to do, where the lines meet behind the mirror. When you see that negative Q, you should know, oh, my lines are going to meet behind the mirror. And the trick to this is that, that first line, and it doesn't matter what order you do the lines in, obviously. So that first line comes in parallel, it's reflected back through focal point. And it is the reflected line that has to meet. Because the image, remember, your image is reflected. It's the reflection line that meets, not the inbound line. So your second line, whatever color you want to use, connects focal point and the object to the mirror. And then the reflected line, again, and that's critical, is the one that's going to meet behind the mirror. Your third line is the one that's connecting center of curvature and the mirror and reflects along itself. So there we have a meeting point. Now, that confirms that it's virtual, so it's behind the mirror. It confirms that it's upright because the point where they meet, the top of the object, is above the principal axis. And it confirms that it's enlarged because the point where they meet is higher, it's higher than the height of the object itself. Now, and I made a note on my key, yes, my drawing confirms all of those things. However, based on my scale, I predicted Q being out here. It's not. So, I suspect for myself, slightly sloppy drawing. And that's why I say the ray tracing, it's just like that vector analysis. You're not going to get an exact number. What you should get is whether it's real or virtual, upright or inverted, enlarged or reduced. The question is, can you have any combination of, real, virtual, upright, enlarged, or upright, inverted, enlarged, or reduced? Probably. There are more common groupings, and there's a whole, the reason I always hated mirrors and reflection problems, because when I was in school, we did these in junior high. Okay, in a concave mirror, with an object that's inside the blah, 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 it forms a real, inverted, magnified. You were expected to just memorize all this, frankly, junk. It never made any sense. Once you have the math, and you know, oh, if this number's negative, it's this. If this number's negative, it's that. If this number's positive, it's that. It's pretty easy. So you could, in theory, memorize real, virtual, inverted, upright, reduced, enlarged for every position, and what it comes down to is Is it behind the center of curvature? Is it between the center of curvature and the focal point? Is it inside the focal point? And there are, you know, standard things for a concave mirror in those three positions. It will be this, this, and this, 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 and this. Just trust your numbers. It's much easier to remember your numbers. And you guys are good with numbers. Other questions on this one? Like I said, getting the lines to meet behind the mirror is the hardest part. Remembering that it's those reflection lines that have to run behind the mirror. Okay, next one. Okay, same mirror. Center of curvature is still 30. We have a tall, 5 centimeter tall object, and it's put 20 centimeters out from the mirror. Again, remembering your P's and Q's, solving algebraically. Whoops, that should just be Q because I already took the inverse. So you get a Q of 60 centimeters. 60.0 is how many sig figs you get. So this thing is real, but it's way out back. It's tremendously far behind the mirror. Magnification, negative 60 over 20, you get a negative 3. So the negative means it's inverted, and the 3 means it's enlarged, and the image is most certainly real. Now, getting this one scaled onto a piece of paper was rather challenging. People came up with creative solutions. Let's look at it. Okay, so we've got our mirror. Center of curvature, focal point. The object is between the center of curvature and the focal point. And remember, it's the reflected rays that you want to have meet up. So here is our first inbound, and it's outbound. Here is our second inbound, and it's outbound. And hey, we got 2 meeting. That's a good sign. And our third, of course, is center of curvature and the object. They come pretty close. I don't, you know, if your lines are making a tiny little triangle like that, I think that's okay. And once again, same thing. I had predicted my Q based on scale was going to be somewhere out here, and I'm a little under Q. That happens a lot. The ray tracing is not a way to get a perfectly mathematical idea of where an image is going to form. It's a way to get a good rough estimate, and it should, if you're doing it right, it will definitely tell you if it's real or virtual. It will definitely tell you if it's inverted or upright, and it will definitely tell you if it's magnified or enlarged. You know, and clearly, if you look at the height of the image versus the height of the object, this is clearly enlarged. It's below the principal axis. It's clearly inverted. Questions, comments, concerns? Yes, sir. So what do you look at to see if it's enlarged or not? 2 things. You look for your magnification, and remember, a magnification greater than 1 means it's enlarged. Magnification less than 1 means it's reduced. No, magnitude of the magnification. Magnitude of the magnification. The sign tells you if it's inverted or upright. So let me do this. Absolute value of the magnification. That helps. Okay. Let me move this thing up a little bit. Yeah. The absolute value of the magnitude of the magnification, greater than 1 is enlarged, less than 1 is reduced. So if you get a magnification of 0.75, that's a reduced image. Yes. Yeah. And you can't have a magnification less than 0. Well, it's absolute value. So yeah, never mind. You can have negative numbers because the negative is what tells you if it's inverted or upright. So sign of the magnification gives you that. Other questions? Okay. So what we're going to do real quickly is start to talk about convex mirrors. It is all the same math. It is all the same ray tracing, but there are a few key differences. So we're going to talk about it a little bit together, and then I'll probably put up a tutorial on the math of convex mirrors and the ray tracing of convex mirrors. I think it's nice to have those just as a reference piece if you want to go back to it.